Hello and welcome to a new video. In the previous video I showed how to generate a frequency modulated signal of a particular FM deviation. Now why that was interesting, in this video I'm actually going to apply what I learned and showed in that experiment in order to calibrate a repeater. This machine here is a full FM repeater for the 70 centimeter amateur radio band, and I'm going to show you how exactly it's made of, what part it consists of, and then we'll actually run the calibration. Now it is important to me to state that this is not my work. There's a lot of work from the HB9UF group that went into this repeater, and the only thing I actually did is that card here that I showed in the DDS video. So anyway, how does that repeater work? The idea is that you've got this connector here, I hope you can see this, and this is a T connector. So the antenna goes to the centerpiece of the T connector, and then there is two cables here, two coaxial cables that go to a transmitter and a receiver. So the idea is that this radio here is receiving whatever somebody wants to transmit via the repeater, and this guy is then transmitting what the receiver received on another frequency. So there is a little problem here, because if this was just hooked up like that with this T connector here, as soon as this guy starts to transmit, it's going to completely overload, and actually it would even break the receiver here, because this is going to transmit at maybe 30 watts or so, and the receiver is very sensitive. It's sensitive in the order of microwatts, so it will completely break the input circuitry here at the antenna connector. And that's why this guy is not directly connected to the two radios, but there is actually one cavity filter here and one down here that you probably can't see in the video. And these two cables here, they go to those two filters, and the filters make sure that first of all, none of the transmit power, or very little of the transmit power, makes it to the receiver, because there is the filter between the receiver and this connector here that ought to block out those frequencies. Now that is one of the reasons why you need two frequencies, one to transmit and one to receive. And this system here is set up such that the receiver is listening on 439.15 megahertz, and the transmitter is transmitting at 431.55 megahertz. So there is a 7.6 megahertz shift in between those two, and that is standard in this region of the world. Okay, so now I discussed the two radios, the two cavity filters here, as well as the RF connector here. By the way, this is also a neat way to actually only use one antenna for those two radios, because somehow you have to combine the two antenna connections here to go to just one antenna. The alternative to that is to use two antennas, which might be easier in some cases, but in most of our cases it is not. So we rely on these two cavity filters here. Now on the right side there is an audio board. These cards all plug into a back plane that is at the back of the unit here. So the radios are actually connected to that back plane, and so are those two cards. And in the end, the receiver will send the received audio to the back plane, which then will make it into that card. The audio will be processed there, amplified or attenuated, and sent back into the back plane, where it gets back into the transmitter and where it is transmitted. So that's the role of that card here, and I discussed this in one of the previous videos. This also generates CTCSS tones and CW automatic IDs and stuff like that. Now this card is the controller card. There is a microcontroller on there. It also plugs into the back plane, and its role is to decide when to key up the transmitter, when to send the automatic ID and things like that. So this is all controlled through the backplane, and this guy here is a power supply. So that's a repeater, and what I want to do is I want to make sure that whatever I transmit into the repeater, which means whatever this guy here, the receiver, is receiving, will be repeated by the repeater as unaltered as possible. In particular, I want to make sure that if there is a signal going into the receiver with a particular deviation, that the repeater is transmitting that signal with the very same deviation. Now there is a bunch of ways to do that. Probably the simplest way is to have a repeater, one radio to transmit a sine tone or something into the repeater, and a second radio, which actually can be just a receiver, where you flip between the input and the output frequency of the repeater and just acoustically compare the loudness of the two tones. So what exactly does that mean? If you think about it, if you tune to the input frequency of the repeater, what you will hear with your radio will be the signal that is sent directly by the guy who is using the repeater. So the repeater is totally out of the equation here. You're just listening directly to whatever somebody is sending into the machine. Now, if you tune to the output frequency of the repeater, you will of course hear the same thing, but not directly from the transmitting radio, but rather from the repeater, from the transmitting radio inside the repeater, which is this guy here. That, by the way, doesn't belong to the repeater. That is just my test setup here, and so is the laptop. So that would be one way, but that is kind of tricky and very annoying to flip back and forth all the time. So I decided to go another way, and I'll go and try to explain that. I have my laptop connected to the CPU card here using a debug interface, and I booted up the repeater in some sort of service mode where I can directly interact with the repeater and switch various things on and off. So what I will do is I will use the exact setup from the previous video to generate a FM signal with a deviation of 3 kHz. I will check that with the computer exactly as I did in the previous video. And then I will listen with the computer and the SDR. I will listen to the output frequency of the repeater and change the gain of the amplifier in here such that I achieve exactly that same 3 kHz deviation that I have on the input. And the reason why this method is a good one is, as you remember from the previous video, I really hope that this will focus here. Let's see. Yeah, nice. So those are these Bessel functions here, and we were trying to hit that null here, that Bessel 0, and you can see that the curve is quite steep, which means that you have to, it is very easy to find this exact spot, because even if you move a little bit to the left or to the right, you immediately have a carrier that is quite large. Before we run the actual calibration procedure, there is one last thing to discuss. I said in the previous video that people have to agree on a particular FM deviation. If they're too wide, then they interfere with neighboring channels, and if they're too narrow, then they're just not loud enough. You hear that they're quieting the receiver, but you barely hear their modulation because you're just too narrow. And we learned last time that a narrow signal, a signal with a low deviation, just means that the modulation itself has a low amplitude, and we don't want to do that. So people in the amateur radio community, they sort of agreed on a sort of wide deviation of 5 kHz and a narrow deviation of 2.5 kHz. But that's a bit confusing, because if you talk to somebody in the broadcasting industry, wideband FM to him has a deviation of 75 kHz or something like that. So there is a lot of confusion with these terms. Also, some people refer to narrow band FM to a frequency modulated signal with a modulation index lower than 1. So I won't use these terms often, but I just want to say that there is like two standards, and one is 5 kilohertz deviation and the other one is 2.5 kilohertz of deviation. And eventually this repeater will run at deviation of 5 kilohertz because that's the standard here in the 70 centimeter band. But if you listen carefully, you noted that I said that I will calibrate this with a deviation of 3 kilohertz. So how can I get away with that? The answer is fairly simple. In the end, I just want this repeater to repeat whatever it gets on the input as unaltered as possible, which means that if somebody comes in with 3 kilohertz of deviation, I want the repeater to repeat that with 3 kilohertz of deviation. If somebody comes in with the proper quote-unquote deviation of 5 kilohertz, the repeater shall repeat that with a deviation of 5 kilohertz. There is maybe two things to note. First, if somebody comes in too wide, I don't really want the repeater to repeat it with that wide a deviation, because the repeater itself would then interfere with neighboring channels, and I kind of don't want to have that. And the other thing I have to be careful about is if I calibrate this with a deviation of 3 kilohertz and I want to run it at 5 kilohertz in the end, I'm not stressing out the amplifier here, because as I repeatedly said, a higher deviation means more amplitude for the baseband signal, and there is the possibility that the amplifier in this board here, there we go, there is an operational amplifier here that does all the mixing and amplifying, and if this amplifier doesn't have sufficient headroom, then things might work well at 3 kilohertz, but there would be distortion and ugly effects at higher a deviation. But I tested that separately, and that is not the case. So let's dive straight into GNU Radio and calibrate this thing. Okay, so I now have the pipeline running, and everything is exactly as it was in the previous video, so there is nothing new here. The first thing I'm going to do is I have now my test transmitter here set to the output frequency of the repeater, and the repeater is off. So I'm just testing whether I really have the proper deviation of 3 kilohertz here. So let me start transmit. Nice, I'm transmitting now. I will center the carrier here as I did last time. Okay, and then I'll add modulation. And you can see that I sort of have this nice sideband pattern here, and also the carrier is almost at 0. So that seems to work out nicely, no problem at all. Now I'll turn off the modulation again and turn off the transmitter. And the next thing I'm doing is I switch the transmitter to the input frequency of the repeater, but the repeater is still off. The reason for that is I just want to make sure that the signal I'm generating with the transmitter is not interfering with the signal that I'm measuring here. So when I turn on the transmitter, nothing should change here. And that is indeed the case, because I just turned it on and nothing changed. So let me turn it off again. And then I will go to the repeater service menu and turn on the transmitter inside the repeater. Now, what you hear is my test transceiver here receiving the noise that is generated by the repeater. That might be a bit confusing, because here I'm in service mode, so if I turn on the transmitter inside the repeater, it's just going to transmit whatever it's receiving, and in this case it's just receiving noise, which is why we're just getting noise here. But we see that there is a carrier here, so things work out nicely. And now if I turn back on my test transceiver without modulation, I should just get a quiet response here. And that is indeed the case. So the noise pattern disappeared, I'm back to my carrier, and I'm actually full quieting the repeater right now. So let me add back modulation, and you see that I get now again, this is not surprising, this sideband pattern. However, the carrier is still here at quite some level. And the reason for that is the repeater is not emitting a signal with 3 kHz deviation. So what I will do is I will increase the gain and hope that I can find this spot where the carrier disappears. I can see the carrier dropping, continue to drop, very nice. So that's already quite good. And now it's rising again. So the Bessel null, I'm trying to get it as good as I can, but it's not very easy. And also I think that the this LO feed through that I talked about last time is in the way here. But anyway, we will do this on a proper service station anyway, but I thought it was fun to kind of pre-calibrate things to get the proper order of magnitude. There is another thing that I want to check, and that is the frequency response of the repeater. So far, all the tests that I've done were at the frequency of 1.245 kHz, because that's the modulation frequency that I have to set to get that 3 kHz deviation. But as I said in the very beginning of the video, I want the repeater to replicate at its output the input as well as possible, which should not only hold true for 1.245 kHz, but actually the frequency response should be as flat as possible, because I don't want to kind of boost any bass or trebles or whatever. It's just supposed to repeat the input to the output as unaltered as possible. Now, to check that, I wrote a little script that will sweep my function generator from 50 Hz to 5 kHz. And first I will look at the frequency response of the test transmitter itself, and I'll record that as a baseline and then compare that to the intensities of the frequencies that I get when it runs through the repeater. So let's try that first. In fact, let's turn on the test transmitter, which is now set to the output frequency of the repeater. So as before, the repeater is completely out of the equation. It's as if it wasn't there. And I will center on the carrier here. There is no modulation right now. And I will turn on this peak hold feature. That will just allow me to have a look at the overall frequency response when I'm done with the sweep. I will add modulation, okay, and I will start sweeping by running this script. Okay, I'll turn on the speaker so that you can hear that. I'm not sure whether you can hear it, but there is basically a tone that increases in frequency, not surprisingly. Note that this also works for very low frequencies here, so there is no cutoff at low frequencies. Then we're now at about 1.5 kHz, and already you can see that the frequency response of this system is extremely flat. This is very nice. What you can also observe is that in the channel spectrum here, the sidebands are increasing, the spacing of the sidebands is increasing, which is exactly what we would expect, and this is also what we saw in the previous video. Now I'll turn off the speaker because this is getting annoying, but basically so far we're at 3 kHz now. That is the upper boundary of relevant frequencies for speech, and the response is extremely flat, so I don't even have to compensate for that, and I can just look at the response through the repeater without taking into account any fluctuation of the transmitter, which is nice because it makes the task a little bit easier. And now we're at 4 kHz and still fairly flat, and I think that the sweep will stop at 5 kHz. So we're almost there. And in fact, what I will have to do when I'm done here is stop the FFT, because as soon as I turn off the transceiver, the noise will increase, and destroy that nice curve that I have here. So let's stop that, turn off the transmitter, and there we go. So that is nice and flat. Basically what we take home from here is that the test transmitter itself does exactly what it should do. It has a flat frequency response. Now, next I will start this again. Now see how this kind of got destroyed here, and turn off the peak hold. And now set the test transmitter to the input frequency of the repeater. And furthermore, I will turn on the repeater. Let's see. Alright. You can hear the fan going. And as before, we have a carrier here and a lot of noise. If we listen to that, we hear how the repeater is repeating this noise. Now let me turn off the modulation and turn on the transmitter. And now I'm full quieting the receiver. Okay, so I will turn back on the peak hold and turn on the modulation and start sweeping. And now we're going to compare this response to the one we got from the test transmitter itself. Now, one interesting difference is that any frequencies below maybe 280 Hertz are attenuated. Let's turn off the speaker here. The reason for that is, remember that I'm generating a PL tone inside the repeater. That's the DDS stuff I discussed a few videos ago. Now, if a user of the repeater were to send his own PL tone, which he actually does, that PL tone would beat against mine, and I don't want that to happen. So I'm just filtering out any PL tones of the user such that I have room to inject my own. And so far this looks fairly good, because I have a very nice frequency response so far, nice and flat. Now I'm hitting 3 kHz, and I expect it to drop now fairly rapidly, which is indeed what is happening. One reason for that is, remember that as the frequency of the modulation increases, the spacing of the sidebands will increase as well. And if I were not to attenuate this and actually have it fully attenuated between 4 and 5 kHz maybe, I would have such a large sideband spacing that I would start to interfere with neighboring channels. So it's kind of always the same story, and that's why I'm attenuating that, and this is safe to do because the interesting stuff is anyway between 300 Hz and 3 kHz when it comes to speech. Okay, so I'm very happy with that. I hope that was interesting to watch, and as usual, if you have anything to comment or to discuss, any remarks, please do so in the comments, and I say thank you for watching.